How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You tap a screen, and a car you don't own arrives to take you wherever you want to go. You speak a question into the air, and a disembodied voice from a speaker on your counter tells you the weather. You type a few words into a search box, and in less than a second, the collected knowledge of humanity on that topic is ranked and presented for you. These are the casual miracles of modern life. We perform them dozens, even hundreds of times a day. Without a second thought, they feel like direct extensions of our will. We want something, we tap a piece of glass, and it happens. The connection is so immediate, so seamless, that we rarely stop to consider the staggering complexity hidden just beneath the surface. We think of an app or a program as a single, magical thing. But have you ever stopped to wonder how that actually works? What is happening in the gap between your finger touching the screen and the real world responding to your command? How can a simple human intention be understood by a machine made of silicon and metal? What are the fundamental rules, the first principles, that translate our thoughts into the actions that power our digital world? Today, we are going to open the most important black box of our era. It's the invisible architecture that underpins almost every aspect of our lives. It's the blueprint for our digital reality, the language that commands our silent electronic servants. Today, we're going to ask a question that is at once incredibly simple and profoundly complex. What is code? To understand the world of code, we first have to appreciate the magic we see every single day. We are surrounded by an enchanted forest of code, and we are so used to it that we no longer see the trees. The software on your phone is obvious, but it's just the beginning. The car you drive is a rolling computer, with millions of lines of code managing everything from the engine's fuel injection to the anti-lock brakes to the infotainment system that plays this very podcast. When you buy a coffee, the transaction is processed by a point-of-sale system running software. That transaction is then communicated to a bank through a network running on servers, all orchestrated by code. The traffic lights that manage your drive home are programmed. The thermostat that adjusts your home's temperature is running a simple program. The watch on your wrist, the television in your living room, the microwave that heats your dinner, they are all animated by these invisible instructions. Airplanes, power grids, financial markets, medical equipment. Our entire civilization is built on a foundation of code. And the experience of it all is, by design, effortless. We don't see the calculations, we just see the result. We don't see the logic, we just get the answer. Software allows us to edit a video with the swipe of a finger, a task that once required dedicated studios with millions of dollars of physical equipment. It allows us to carry the entire corpus of human knowledge in our pocket and search it in an instant. It feels like we have been given superpowers. We can communicate, create, and navigate the world in ways that would have been utterly indistinguishable from sorcery just a century ago. This feeling of empowerment, of direct and effortless control, is the magic we see, but it is a beautifully crafted illusion. To understand what's really going on, we have to rewind the clock. We have to go back to a time before software, to understand the monumental problem that code was invented to solve. Before digital computers, a computer was a person. Usually, a room full of people, armed with paper, pencils, and mechanical calculators, performing complex calculations in painstaking, repetitive steps. Machines existed, but they were not programmable in the way we think of it today. They were built for one purpose. A mechanical calculator could add and subtract, but it couldn't guide a missile or play a game of chess. Its logic was baked into its physical structure, its gears, its levers, its cogs. The dawn of the electronic age brought machines like ENIAC, one of the first general-purpose computers. It was a monster, filling a massive room with vacuum tubes and tangled wires, and programming it was a brutally physical act. There was no screen, no keyboard. To give ENIAC its instructions, engineers had to physically rewire it. They would unplug thick cables from one socket and plug them into another, manually connecting different parts of the machine to control the flow of calculations. A single program could take weeks to set up, a painstaking process of translating mathematical formulas into a physical wiring diagram. This was the fundamental problem, the great chasm that needed to be bridged. On one side, you have us humans. We think in language, in ideas, in abstract concepts like find the fastest route or make this photo look warmer. We think in logic and narrative. On the other side, you have the machine. A computer processor, at its most fundamental level, is a rock that we tricked into thinking. It is a piece of silicon etched with billions of microscopic switches called transistors. Each switch can be in one of two states, on or off. That's it. There's nothing else. We represent these two states with a 1 for on and a 0 for off. The machine understands one thing and one thing only, a sequence of these ones and zeros. It understands electricity. It doesn't understand blue or louder or friend. It understands patterns of electrical pulses. So the great challenge was this: how do you bridge the infinite gap between the rich abstract world of human thought and the stark, unforgiving binary world of the machine? How do you tell a rock what you want it to do? Manually plugging in wires wasn't a sustainable solution. It was too slow, too rigid, and too prone to error. We needed a better way. We needed a language. This is where we open the box, and the first thing we find inside, the most important concept in all of computer science, the first principle that makes everything else possible, is a single idea: abstraction. Abstraction is a word we use all the time, but in this context, it has a very specific and powerful meaning. It means hiding complexity to make something easier to use. You do this every day. When you get in your car, you turn a key or push a button, you press a pedal to go, and you turn a wheel to steer. You are interacting with a very simple interface: pedals, wheel, ignition. This is an abstraction. Underneath that simplicity is a staggering amount of complexity. The chemical reactions in the battery, the controlled explosions inside the engine cylinders, the hydraulics of the brake system, the intricate gearing of the transmission. You don't need to know how any of that works to drive the car. The complexity is hidden from you. The car's designers have provided you with a high-level abstraction. Code is the ultimate expression of this idea. It is a series of abstractions, layered one on top of the other, that allows a human being to communicate with the machine without ever having to think about the billions of switches flipping on and off. To understand this, let's use an analogy. Let's imagine the task we want the computer to perform is not an app, but a great work of literature. Let's say, a beautiful poetic novel written in French. The novel is rich with meaning, nuance, and complex ideas. This novel is our goal. It's the app we want to create. Now, imagine the person who has to perform the task, the one who has to bring this novel to life. This person is our computer processor. But there's a catch. The processor doesn't speak French. It doesn't speak English, or Spanish, or any human language at all. In fact, it can't even read letters. The only language our processor understands is Morse code, dots and dashes. That's it. Our problem is clear. How do we get the rich, poetic meaning of the French novel faithfully translated into a long, long sequence of dots and dashes? You wouldn't do it in one step. A direct translation from poetic French to Morse code is so complex, so difficult, that you would almost certainly make mistakes. It's just too big of a leap. So what do? You use abstraction. You create layers of translation. Your first step might be to hire a translator who is an expert in both French and English. This translator takes the original French novel and produces a very literal, straightforward English version. All the poetry might be lost, but the core plot and the meaning are preserved. The language is now simpler, more structured. This is exactly what the first layer of code is. It's called a high-level programming language. Languages like Python, JavaScript, Java, or C++, when a programmer sits down to write code, they are not writing ones and zeros. They are writing in one of these high-level languages. A programmer might write a line of code like "print, hello world." This is an instruction that is designed to be readable by a human. It looks a bit like English. It has words and symbols that we can understand. This is our French novel. It expresses the programmer's intent, their idea, in a language that is abstract and far removed from the machine's internal workings. The programmer writing "print, hello world" doesn't need to know how the screen physically displays pixels, any more than a driver needs to know about engine combustion. They are working at a high level of abstraction. So now we have our story written down in this human-readable language. But the computer still can't understand it. We have our novel in English, but our processor only understands Morse code. This is where we get to the heart of the matter. This is the magic black box that makes the modern world possible. We need another translator. In the world of software, this master translator is a special program called a compiler, or in some cases an interpreter. The compiler is one of the most brilliant inventions of the 20th century. Its job is to take the human-written source code, that text file filled with "print" statements and "if" conditions, and translate it, methodically and perfectly, down into a language the machine can understand. It is our expert translator. So, the programmer finishes writing their code, their novel. They then hand this text file to the compiler. The first thing the compiler does is read the entire thing, checking for errors. It's like an editor proofreading the novel. Does the programmer have any spelling mistakes? Is the grammar correct? In programming, this is called syntax. If you write "print, hello" instead of "print, hello," the compiler will stop and report a syntax error. It enforces the rules of the language. Once the compiler is satisfied that the source code is written correctly, the real translation begins. And just like our novel analogy, it often happens in stages. The high-level language, our English novel, is first translated into a lower-level language. A common one is called assembly language. Assembly is our next step down the ladder of abstraction. It's much closer to what the machine actually does. It's like translating the simple English novel into a set of brutally direct, simple instructions. Something like, take the number 5, put it in box A, take the number 10. Put it in box B, add the contents of box A to box B, put the result in box C. In real assembly, it looks something like this: "mov ax 5 " This means move the value 5 into a storage location called ax. It's cryptic to us, but it's a much more direct command for the processor. Each line in assembly typically corresponds to a single basic operation the processor can perform. We've lost all the elegance of the original language, but we are one giant step closer to the machine's native tongue. We have translated our English novel into a hyper-literal, step-by-step instruction manual. We're almost there. We have our instructions in assembly language, but the processor still can't read it. It doesn't understand the letters "mov" or "tad". It only understands ones and zeros, Morse code. So we need one final, tiny translation step. This is done by another program called an assembler. The assembler's job is the simplest of all. It takes the assembly code, like "MOVAX, 5 and translates it into the final product. Machine code, it converts each of those simple mnemonics into the specific sequence of ones and zeros that the processor understands. "MOVAX, 5 might become something like "1011100000000101". And that is it. That is the destination. A long, long string of ones and zeros, dots and dashes. This is the only thing the computer can actually execute. This binary file is the finished product. When you download an app from the App Store, you are not downloading the human-written source code. You are downloading this final, compiled machine code version. This is the moment for our first real, aha moment. Every single piece of software you have ever used, the operating system on your computer, the web browser you're using, the game you play on your console, the app you tapped on in the coffee shop, every single one started its life as a simple text file, a document written by a human being in a language that looks more like English than like binary. That text file was then fed into a compiler, which acted as a tireless perfect translator, converting that human-readable blueprint, layer by layer, down into the raw, electrified language of the machine. The magic is a process of translation. And this reveals one of the most common misconceptions about code. People often think that the code a programmer writes is what's running. They see a line like "color equals blue," and imagine the computer is directly reading and understanding that line. But that's not true. The source code, the text file the programmer writes, is completely inert. It doesn't do anything on its own. It is just a recipe. It's a blueprint. It has no power until the compiler has read it and translated it into the machine code instructions. The text file is the sheet music. The compiled program is the orchestra performing it. The source code is the recipe. The machine code is the baked cake. Without the translator, the human's instructions would remain forever unheard, just silent words in a text file, and the machine would sit there, a powerful but ignorant rock. So, we've bridged the gap. We have a process to turn our abstract human ideas into the concrete binary instructions a processor can execute, from French novel to simple English, to a literal instruction manual, to Morse code. But there's one more piece to this puzzle, a final layer of abstraction so fundamental, so ubiquitous, that we don't even see it. It is the unseen giant upon whose shoulders all of our software stands. Let's go back to our program. We've written our code, compiled it down to machine code, and now we're ready to run it. Our little program wants to do something simple. It wants to display the words "Hello World" on the screen. The machine code contains the instructions to do this. But how? How does a program actually control the physical screen? Does the machine code contain the specific commands for your particular brand of monitor? Does it know how to talk to the graphics card you have installed in your computer? What if the program wants to save a file? Does it need to know the intimate details of how your solid-state drive stores data? What if it wants to send a message over the internet? Does it need to contain all the code for managing a Wi-Fi connection? If this were the case, it would be a nightmare. A programmer would have to rewrite their code for every single possible combination of hardware in the world. An app that runs on one phone wouldn't run on another if they used a different screen or a different networking chip. It would be chaos. This problem is solved by the most important piece of software on any device, the operating system, or OS. Your Windows, your macOS, your Android, your iOS. This is the true master of the machine. The OS is the ultimate gatekeeper, the traffic cop, the resource manager. It sits between all your applications and the physical hardware. When your compiled program wants to do something like write on the screen, it does not talk to the screen directly. That is forbidden. Instead, it makes a request to the operating system. It sends a message that essentially says, "Excuse me, Mr. Operating System, I have this text, 'Hello World. Would you be so kind as to display it for me?'" The operating system takes that request. The OS is the only one who knows the specific details of your hardware. It knows what kind of graphics card you have, and it has the special programs called drivers that know how to talk to it. So the OS takes the "Hello World" text and translates it into the very specific machine code commands needed for your exact hardware, and it sends those commands to the graphics card, which then draws the pixels on the screen. This is the final, and perhaps most profound layer of abstraction. The programmer doesn't need to worry about hardware at all. They just need to know how to ask the operating system for things. The OS provides a consistent, stable set of services that any application can use. It provides a function to draw on the screen, a function to save a file, a function to play a sound, a function to send network data. This creates a stable platform, a virtual sandbox where our programs can run. It's why you can run the same web browser on a Dell, an HP, or a custom-built PC. The browser isn't written for Dell hardware. It's written for the Windows operating system. As long as the computer is running Windows, the browser knows it can make the same requests and get the same results. The operating system is the silent hero of computing. It manages memory, making sure your web browser doesn't interfere with your music player. It manages the processor, giving each running application a tiny slice of time, swapping between them so quickly that it feels like they are all running at once. It is the conductor of our digital orchestra, ensuring that every program plays its part without getting in the way of the others. It is the foundation upon which our entire digital experience is built. So, let's retrace our journey. We started with the simple, magical act of tapping a screen. We dove beneath the surface and found that this magic wasn't magic at all. It was a conversation. It began with a human being, a programmer, writing down an idea in a high-level language, a text file that was as much for other humans as it was for the machine. We saw that this text file was inert, a mere blueprint, until it was handed to a master translator, a compiler. We followed that compiler on its journey, translating the rich abstract language down through layers of decreasing abstraction, from a high-level language like Python to a more literal language like assembly, and finally, all the way down to the raw binary of machine code, the only language the processor truly understands. The ones and zeros, the dots and dashes, and then, just as those instructions were about to touch the hardware, we found a final gatekeeper, the operating system, the unseen giant that manages the entire performance, providing a stable stage for our programs and handling their every request to interact with the physical world. The first principle of code, the irreducible truth that makes it all possible, is abstraction. It is the brilliant human invention of creating layers of simplicity to tame an ocean of complexity. We build our digital world not like a single monolithic skyscraper, but like a series of Russian nesting dolls, each layer hiding the complexity of the one within it, allowing us to focus on just one level of the problem at a time. The app developer doesn't need to think about machine code. The compiler writer doesn't need to think about the physics of transistors. Each layer provides a foundation for the next. Understanding this journey from thought to thunder changes how you see the world. That app on your phone is no longer a mysterious, magical box. It is the end result of a long and beautiful process of translation. It is a human idea, carefully expressed in a formal language, and then methodically converted into a form that a machine can execute. Code is not a mystical force, it is a medium for human expression, a tool for embedding logic and intent into the inanimate objects around us. It is the most powerful language ever created, allowing us to scribe our thoughts not just onto paper, but into the very fabric of our world. Every time you send a message, play a song, or follow a map, you are witnessing the final echo of a conversation, one that began as words in a text file, a quiet thought in a human mind.
You've been listening to First Principles. Until next time, stay curious.